This video will cover classification and regression trees. By the end of this video, you should have an understanding of what classification and regression trees, or CARTs, are, how CARTs create predictions, and how CARTs can differ from modeling tools like OLS. So far, every modeling tool we've considered assumes the features have a linear relationship with the label. This is really restrictive. Remember, we often think we don't know ahead of time what the true underlying relationship looks like, and assuming it's linear is a strong assumption. What if the true relationship is nonlinear? We can add polynomials of our features, but this can lead to models that become very complex and prone to overfitting. Could we do something else? We could just completely do away with the linearity assumption. Instead, we could assume that the label is some arbitrary function of the features, like this expression I have here. But allowing an arbitrary relationship leads to too much complexity, and again, we could overfit our models. We want a way to be flexible, but also discipline the model selection process to avoid overfitting. Classification and regression trees are a class of modeling tools that replace the linear functional form assumption. They generally present some advantages. In most cases, they have a relatively simple implementation. They make very weak assumptions about the underlying relationship between the features and the label. And more advanced algorithms follow a disciplined approach with very good out-of-sample forecast performance. There are some disadvantages too. Forecasting from these models is often a black box. It's very difficult to tell how exactly the features are being translated into a predicted label. Most CART algorithms rely on several hyperparameters that need to be tuned via cross-validation during the model training process. This, along with some other computational complexity, means that training and evaluating models can be very compute-intensive and can take a very long time. So how do CARTs work? These algorithms generate forecasts using a tree-based structure. The simplest of the CART algorithms is a regression tree. This is the tool that we'll consider in this video. A tree consists of many leaves. The values of features in your model lead you to a specific leaf in your regression tree, and each leaf is going to predict a value of the label as the average value of all the training data labels that are in that leaf. It's probably good to think of a concrete example. So suppose I have a bunch of books. I know each book's width, height, and number of words. I'd like to construct a model to tell me how many words are in each book. So suppose I do the following. I just choose some cutoff height for the books. Let's say 8 inches. I put all the books that are shorter than that on the left and all the books that are taller on the right. With the data that I have, what would my best forecast be for the number of words in a book that is less than 8 inches tall? That best guess is actually just the average of all the books that fall into that bucket of being less than 8 inches tall. And this is exactly how the regression tree works. I start with my set of all books, and then I divide them into two groups, those that are taller than 8 inches and those that are shorter. My best guess of the number of words, or my forecast of the number of words in those books, is just the average number of words in each group. So in my not real example here, books less than 8 inches tall, the average number of words is 10,896, and if I encounter a book that is less than 8 inches tall, that would be my forecast of the number of words. Regression trees are a bit more complicated than just this one division of your data, but there's a simple procedure for training these models. You take all of your data, and you choose a split in the data. You select one feature, and you choose a point. All of the observations with values of that feature that are larger than that split, you place in one leaf, and all the observations with smaller values, you place in the other leaf. Your forecast is the average value of the label for all of the observations in that leaf. Choosing the split, both the feature and where you would split it, might seem like a complicated process. There's actually an algorithm that you can use to choose which split minimizes the in-sample loss. And in fact, if mean square error is your loss function, there's a very simple formula for doing this. So far, we've just split our data into two leaves. Could we do better than that? Of course we could, just by making more splits. So in this example, I've added a second level of splits. The first leaf, the books that were shorter than 8 inches, there's a second split looking at the width, splitting at the point where books are 6 inches wide. Books less than 8 inches tall and 6 inches wide have an average of 7,381 words. In contrast, books taller than 8 inches but less than 9 inches tall have an average of 16,384 words. The important thing to notice here is the feature that I use to split at each level can be different across different leaves. So to refine this procedure a little more, if we're constructing a regression tree, we're going to choose a split using one feature in our data. Again, there's an algorithm for that. But then we're going to continue to repeat this process for each leaf, continuing to split it into smaller and smaller sub-leaves. We'll stop adding leaves at some point, and then we'd like to make forecasts. They're the mean value of the label within each leaf. Let's look at a slightly more realistic, but still very simple version of what a regression tree might look like. Notice here that not every leaf is the same distance from the top. This is very common in regression trees. Again, each of these splits will be along one of my features, either the height or the width of the book. and the number in each of the terminal leaves is the average value of the label of all observations that fall into that leaf in my training data. So suppose I have a book that's 9 inches tall and 7 inches wide. What would I forecast for the number of words in that book? Starting with my set of all books, I'll compare it to the first split. The book is taller than 8 inches, so I move to this next leaf here. Looking at the next split, the book is exactly 9 inches tall, so it would fall on the right-hand side. Looking at this leaf here, there's another split below it. The book is 7 inches wide, which is larger than that 4-inch split, so I would fall into this leaf here, and my predicted value for the number of words would be 32,157. As a second example, suppose I have a book that is 7 inches tall and 7 inches wide. Looking at the first split, it's less than 8 inches tall, so we would move to this leaf. We would then compare its width to the 6-inch split. It is larger than 6 inches, and so we end in this leaf here, and our predicted value for the number of words would be 18,925. The important things to take away from these examples are that a regression tree is a tree-like flowchart ending in leaves. Each branch is going to split the data in the leaf above it based on the value of a single feature. Forecasts from this model are the in-sample average of all observations within a given leaf. Regression trees specifically, and CART algorithms in general, divide data into leaves, and that means they can approximate complicated relationships between the features and the labels. In many CARTs, but not all of them, the prediction is the average value of all the training data labels within a particular leaf. This means that CARTs can't make predictions of values outside the range of observed values. This might seem like it's a limitation, but it actually means that CARTs tend to have really good out-of-sample forecast performance because they're not prone to forecasting extreme values. In CARTs, the model complexity is often characterized by the number of leaves. In previous models, we thought of it as the number of features. So be aware that more leaves can lead to a more flexible model, but one that is also overfit. Imagine, for example, that we have one leaf for every training data observation. Our model would be incredibly flexible, but would also have highly variable predictions that might not perform so well out of sample. Many CARTs actually include regularization as part of the training process. With CART algorithms, you generally think of regularization as limiting the number of leaves. I've discussed regression trees here because I think they give really good intuition as to how CART algorithms work. We're not actually ever going to train a regression tree model in R because in reality, they don't perform very well for forecasts. With regression trees, you'll often get a leaf that's based just on a few odd observations. And this means that they're going to have relatively poor out-of-sample predictions in some cases. Other CART algorithms take steps to address these specific problems with regression trees and have improved out-of-sample forecast performance. We'll cover one of those improved models, random forests, in another video.